So here is the problem. So we are told to consider a steady state laminar flow of an incompressible Newtonian fluid with constant density rho and viscosity mu through a circular pipe of radius r and length L. The fluid is driven by a constant pressure gradient where the pressure at entrance at z is equals to 0 is P naught and the pressure at the exit is z is equals to L at PL. Therefore, we need to derive an expression for steady state velocity profile Vz using two methods. First, we will try with the shell momentum balance. So let's go shell momentum balance. So first we will write basics. So as it is Newtonian fluid, so we are told with constant density and constant viscosity. Flow we assume steady state laminar flow. So for cell selection, the inner radius is equals to r, whereas the outer radius is equals to r plus the change in radius, that is r plus delta r. So we assume the thickness is around del r and the length is del z. So according to the momentum balance equation, momentum balance equation, so it says the rate of momentum in minus rate of momentum out plus the sum of the forces is equal to 0. So we will consider the first momentum enters the inner surface of shell R due to slow fluid inside pulling on it. That is area momentum enters inner surface of shell at R. That is area momentum is equals to area into shear stress, that will be 2 pi r into del z will be the area circumference into del z area into the momentum of r, and momentum leaving out will be 2 pi r del z. Similarly, area into tau r z at z. This is r, this is z. Okay. So momentum leaving out should be r plus del r. So we will consider now for pressure forces. The force pushing the liquid in at z is equal to 0. So force pushing the liquid or fluid, whatever we can say, in at z is equal to 0 will be cross sectional area into the pressure. So here cross sectional area is equals to 2 pi r del r into pressure P naught. Okay. Force pushing out will be at z is equal to L, it will be around 2 pi r del r, it will be multiplied by PL, with ZL पे PL pressure है. So by formulating the equation, we get in 2 pi r del z tau r z at z tau r z r minus 2 pi r into del z multiplied by tau r z r plus delta r. plus the pressure equation 2 pi r del r into P naught minus 2 pi r del r into PL is equal to 0. So we create a differential equation. So we r tau r z at r plus del r minus r tau r z at r divided by del r is equals to P naught minus PL by del z multiplied by r. Basically we try to create such a differential equation form by dividing by del r. Del r del z. Okay. So by limiting the equation, limit del r tend to 0, this turns the left side of this into a derivative which can be again rearranged as d of tau r z by dr is equals to P naught minus PL by r by L. Solving for the shear stress profile, we basically integrate both sides with respect to r. That is, integrating, we get r tau r z is equals to P naught minus PL by L into r square, or this r square 2 here plus C1, and again integrating, therefore tau r z is equals to P naught minus PL by 2L into r plus C1 by r, taking this r on this side. Boundary condition. So here boundary condition 1, at r is equal to 0, shear stress must be finite. Shear stress must be finite. Therefore C1 must equal to 0, must be 0. Final shear stress equation becomes, final shear stress equation is equals to tau rz is equals to P naught minus PL by 2L into r. Solving for velocity profile, trz is equals to minus mu by dvz by dr. Substitute this into our shear stress equation, we get minus mu dvz by dr is equals to P naught minus PL by 2L into r. So after taking this here, r this side, and integrating both sides, we get Vz is equals to minus P naught minus PL by 4 mu L r square plus C2. So boundary condition 2, at r is equals to r, Vz is equals to 0. Therefore 0 is equals to minus P naught minus PL by 4 mu L r square plus C2. Therefore we get C2 is equals to P naught minus PL r square by 4 mu L. Okay. So final equation, if we substitute C1 and C2 back there, final equation we get is equals to Vz in function of r, P naught minus PL by 4 mu L r square, and here 1 minus r by r square. So continuing with the second, this is the final first equation. If we solve with the same with the equation of change, so basic state, the steady state, therefore the d by dt is equals to 0. The incompressible fluid, therefore density is constant, Newtonian fluid viscosity constant. Asymmetric flow, therefore we can assume asymmetric flow where d by d theta is equals to constant and dz is equals to 0. So assuming there is no gravity force in that direction. Okay, so we can start with the equation of quantity in cylindrical coordinates, that is 1 by r d by dr r v r plus 1 by r dv theta by d theta plus dvz by dz is equals to 0. So because vr is equals to 0, vr is equals to 0 and v theta is also 0, the first two terms disappear. We are left with dvz by dz is equals to 0. This proves the flow is fully developed. The velocity profile does not change as we move down the length of the pipe. Therefore, using the Navier-Stokes Z component equation, Navier-Stokes for Z component, we call this same as the equation of motion. So next we write the full Z component of the Navier-Stokes equation in cylindrical coordinates. So assuming cylindrical coordinate system, okay. Here we can write the equation is rho dvz by dt dr into dvz by dr plus v theta by r dvz by d theta plus vz dvz by dz is equals to minus dou p by dou z plus mu 1 by r d by dr r dvz by dr plus 1 by r square d square vz plus dt square plus d square vz upon dz square. So here dvz is equals to 0 as we assume steady state, vr is equals to 0 and v theta is equals to 0 because of unidirectional flow. dvz is equals to 0 due to fully developed flow by continuity, and d square vz by dt square is equals to 0 because asymmetry. d square vz is equals by dz square is equals to 0, derivative of a constant is always 0, and dz is equals to 0 because no gravity forces along z direction. So we are left with 0 is equals to minus dou p by dou z plus mu by 1 by r d by dr r into dvz by dr. Okay, so rearranging to isolate the velocity terms so we can integrate it better way. So dou p by dou z is equals to mu 1 by r dA by dr r into dvz by dr. So now we have changed the partial derivative dou to exact derivative d on the right side because vz is now the function of r. So therefore the left side of the equation is a function of z only, while the right side of the function is a function of r only. The only way this mathematical equality holds true for all values of r and z is both sides equal same constant. Therefore pressure gradient is constant and linear. Therefore dou p by dou z is equals to pl minus p naught by l is equals to minus p naught by pl by l, where p naught is the inlet pressure and l naught is the outlet pressure and l is the length of the pipe. So in multiplying both sides by r and mu, therefore d by dr. So we are basically trying to convert this equation. dz by dr is equals to minus p naught minus pl by mu l into r. Integrate with respect to r. So we get r dvz by dr minus p naught minus pl by 2 mu l r square plus c1 divided by r on to isolate the velocity gradient. Actually we need to take this r this side, so we are remaining with dvz by dr is equals to minus p naught minus pl by 2 mu l. Here will be r plus c1 by r. So boundary condition 1, at the center of the pipe the r0 velocity gradient must be finite. Therefore r equals to 0, velocity gradient must be finite. Application of equation, if we assume this, then dvz by dr equals to minus p naught minus pl by 2 mu l r. This we are remaining with this. So integrating again this equation, taking this dr this side and integrating it, we get integration. We are left to dvz is equals to minus p naught by pl 2 mu l r square, this 2 here, so 4 plus c2. So boundary condition 2, we are left with no slip condition. no slip boundary condition, that is R is equals to R, Vz is equals to 0. So if we apply this condition in the equation, we are left with 0 is equals to minus P naught minus PL by 4 mu L R square plus C2, that is we are remaining with C2 is equals to P naught minus PL by 4 mu L R square. So final velocity equation, if we put C1 C2 in that, final equation would be Vz is a function of R, where P naught minus PL by 4 mu L R square in 1 minus R by R square. This is the final. So here is the next question. The composite we are given. The composite wall shown below consists of materials A and B with thermal conductivity K is equals to 10 watt per meter Kelvin and Kb is equals to 0.8 watt meter per Kelvin. If the surface area of the wall is 5 meter per second, determine the internal interface temperature between A and B. We are about to determine the temperature at this point. So the given data is equals to Ka is equals to 10 watt per meter Kelvin and Kb is equals to 0.8 watt per meter Kelvin. Okay, so La we are given 10 centimeter. Yes, 10 centimeter is equals to 0.1 meter, and LB we are given upon 0.2 meter. So temperature of the outlet was equals to 14 degrees, 40 degrees Celsius, whereas the outer wall is 14 degrees Celsius. So we are here 40 degrees Celsius. We will call this T1 is equals to 40 degrees Celsius, T3 is equals to 14 degrees Celsius. Okay, fine. So the goal is to find the interface temperature between A and B, and the area we are given 5 meter square. So setting up the equation using the Fourier steady state law, for the rate of heat transfer is constant through all the layers. Therefore QA is equals to QB from Fourier's law. Therefore its law said Ka into A T1 minus T2 divided by La is equals to Kb into A into T2 minus T3 by Lb. So we can cancel out the area from the add is 5 equal, so we can cancel out the area. The equation remains at Ka T1 minus T2 by La is equals to Kb Lb into T2 minus T3. So we are about to count T2. So if we substitute the numbers as K is equals to 10, A length 1 0.1, 40 minus T2 is equals to 0.8 by 0.2 into T2 minus 14. So as if we solve this equation, we get 100, 40 minus T2 is equals to 4 into T2 minus 14. Solving for this divided by 25, we can 4000 minus 100, T2 is equals to 4, T2 minus 14 for the 56. So if we take this side, 4056 is equals to 104 T2. So T2 is equals to 4056 by 104. T2 is equals to 4056 divided by 104. It's around 39 degrees Celsius. So the temperature between A and B is exactly 39 degrees Celsius. So here is the fourth question. We are given a furnace wall consists of a 3 layer. The first layer is layer of heat resistance or refractory. The layer of refractory insulating brick with the steel plate of 0.25 inch thick for protection. Calculate the thickness of each layer to give minimum total wall thickness if the heat loss to the wall is 5000 BTU per feet square. Okay, we are given the data of the materials, like 3 kind of materials: the maximum allowed temperature, thermal conductivity at 100 and 200 degree Fahrenheit. Okay, so we approach it by the problem asks us to find the thickness of true break layer that result in minimum total wall thickness while maintaining a constant heat flux of 5000. I guess I'm wrong. 5000 BTU per year. Okay. To minimize thickness, we must use as much as best insulator as possible. Looking at the table, the insulator brick has much more lower thermal conductivity, as we can see 0.9 and 1.8, than the refractory brick. Therefore, we want to maximize the thickness of insulating brick. Here, let's define some variables. Is equals to inner wall temperature T naught. We can set this to maximum allowable temperature of refractory brick, that is 2600 Fahrenheit, is equal to 2600 Fahrenheit. Okay, so T1 we define at interface of refractory and insulating brick. Interface of refractory and insulating brick. We can set this to maximum allowable temperature of the insulating brick, that is 2000 degree Fahrenheit. Okay, so T2, the interface of insulating brick and steel, we need to find this. Let's define this too. T2 is equals to interface of insulating brick and steel. Okay, and T3 is the outer surface to steel plate. Okay, temperature drop across the steel plate. First we find T2 by calculating the temperature drop across the steel plate. Therefore, heat flux is equals to Q is equals to 5000 BTU per feet square. Steel thickness is equals to, that is L3 steel thickness 0.25 inch, that will be around 0.02083, yes, 0.0283 feet. Steel thermal conductivity and K3 we have found at 26.1 BTU per hour feet degree Fahrenheit. Using the Fourier's law, we can define Q2 is equals to Q is equals to K3 T2 minus T3 by L3. So heat flux is equals to K delta T by L. Okay. By T 26.1 into T2 minus 100 by 0.02083. We can write this as T2 minus 100 is equals to let me calculate. Around 3.99 degree Fahrenheit, that is T2 will be around 103.99 degree Fahrenheit. Calculating the heat thermal conductivities, because thermal conductivity varies linearly with temperature, we can evaluate K at arithmetic mean temperature of each layer. Therefore, for refractory layer, brick layer L1, mean temperature T mean is equals to 2600 plus 2000 by 2 is equals to, it is around 2300 degree Fahrenheit. So by interpolating we get actually the slope will be 3.6 minus 1.8 by 2000 minus 100, 0.000974. So K1 by interpolating is equals to 1.81 0.009474 T minus 100. That is, we get K1 is equals to 3.884 BTU per hour degree Fahrenheit. This will be for the refractory brick layer. Similarly, we can solve the same for insulating brick layer. L2 T equals to 2000 plus 2.99 by 2 is equals to 1052 degree Fahrenheit. By interpolating the same, we get slope is equals to 1.8 minus 0.9 by 0.00417, and therefore we get K2 is equals to 0.92. One more zero. 1052 minus equals to 1.89. Okay, and finally for calculating the thickness of each brick layer. So calculating refractory, now we apply Fourier's law to each layer to find the thickness. Therefore Q is equals to K1 Fourier's law T0 minus T1 by L1, that will be 5000 is equals to 3.884 into cosine double minus 2000 by L1. L1 is equals to 3.884, 600 by 5000 is equals to 0.4661. So it will be around 5.59 inches, because 1 feet equals 12 inches. And insulating brick layer thickness, we get Q. Similarly, Fourier's law is equals to K2 T1 minus T2 by L2. 5000 is equals to 1.35 3.99 divided by L2. We get L2 is equals to 1.351 multiplied by 1896.01. Converting this, it will be around 6.15 inches. So to achieve the minimum total wall thickness under given conditions, we need refractory brick around 5.59 inch thick and insulating brick around 6.15 inch thick. Thank you.